Okay, so I propose we start as we are a bit late. So good afternoon to all of you, and welcome to this first session, actually, of the RTR, which is on air quality and particle emissions. So my name is Alexandru Ghiurca, and I'm a project advisor at CINEA, so the Climate Infrastructure and Environment Executive Agency of the EU. As I mentioned, so this is the first session on air quality and particle emissions. So I will first give you a very short introduction and overview of this session, and then you see we have quite a diverse panel who will guide you through the results of some of the projects that we financed under Horizon 2020 and Horizon Europe as well. So you all know that the EU is very much committed to reducing greenhouse gas emissions by 2030, but also to becoming climate neutral by 2050, but also reducing all forms of pollution and also preventing and preserving human health. It's also without surprise to you that transport emissions still represent a major source of emissions, in particular in urban areas. And also in this context, therefore, it's imperative to have very high quality data and also better knowledge and understanding of how these transport-related particles interact in the atmosphere, what drives their toxicity, what is the potential impact on human health when we develop these prevention policies and we improve the urban air quality. So the projects that we'll present today, they all helped us with this to respond to these policy priorities of the EU. So you will hear from the projects nPETS and lOwNoise, who were financed under Horizon 2020, actually in a topic dealing with the understanding and the mitigation of the effects on public health of emerging non-regulated nanoparticle emissions issues and noise. So the project nPETS, actually, who worked on transport nanoparticles, while the project lOwNoise, so they are both finished right now, who worked on the reduction of noise and particle emissions from Tyres. And they helped also in all these fields, so basically contributing to policy work, but also understanding better the impact of the particles on human health and so forth. And then we have two other projects, EASVOLEE and PAREMPI, who are ongoing, and they all contributed under a topic on preventing smoke emissions in Europe, air quality impact of engine emitted volatile, semi-volatile, and secondary particles. So again, to better, first of all, to better understand the role of the particles, the formation of secondary particles, to provide input to policies as well, and to quantify transport externalities. So without further ado, I will give the floor to my colleagues who will present you the results of the projects. So from the nPETS projects, we have with us Ulf Olofsson, who is professor in tribology at the Royal Institute of Technology in Stockholm, Sweden. For lOwNoise, we have Juan Jesus Garcia from IDIADA, Spain. For EASVOLEE, we have Spiros Pandis, professor in chemical engineering at the Department of the University of Patras, Greece. And from PAREMPI projects, we have Päivi Akko-Saksa, who is the principal research scientist in the research area of exhaust emissions at VTT in Finland. And I have the pleasure to have with me as well my colleague Leonidas and Ntziachristos from the Laboratory of Applied Thermodynamics in Greece, who will also lead the discussion in the second part of the meeting. So I will give the floor to each of the presenters. So each of you would have 15 minutes for their presentation. And then if you have any questions for clarifications, you can ask them at the end of each presentation. Otherwise, we have a more dedicated discussion session in the second part of the meeting. So Ulf Olofsson, please, you have the floor.
So, thank you. I will talk about the nPETS project that was actually finalized in November 2024. And we have been looking into nanoparticle emissions from the transport sector. And to start with, this is the background for me when we started to draft the proposal. This is the emissions in terms of particle number in a street canyon in Stockholm, the black line. And you can see particle number from roughly 2000 until now. You can see a decrease from around 90,000 down to 15,000 during this time span. and I've also marked the different Euro legislation implementations. And looking into the fleet renewal rate of around 15 years, this is doable. But we are still above the WHO high limit proposal, that is 10,000 particles per cubic centimeters. So we are still above that level. And you can see on the bottom line, that is what we have in a very forest part of Sweden. The gray line, that's around 3,000 particles per cubic centimeter. And also the urban background line for Stockholm. So my question was, and the idea behind it, is this enough? And the way we have attacked this is that we have an impact pathway to assess the health and economic impact of these emissions. We have looked into from road transport, rail, sea and air, how much particles do we actually produce in the normal size range from these transport sectors. So we measure that, and then we have modeled that by dispersion modeling in 4 different cities around Europe. We have used toxic scoring to see how did this affect health. We have a dose response effect, and we have also looked into what is the monetary impact of this and how can this be implemented. So field campaigns, we have been measuring in Barcelona, Stockholm, Saloniki, and Milan, and we have looked into road, rail, air, sea, and also urban background. Mapping both winter and summer campaigns. We have used the same instrumentation of all sites, just to be sure that we can compare the numbers. So we have measured the parting numbers, but also the toxic effect in the same way. And yes, we see nanoparticles at all field measurement sites. And here you see a diagram showing the result from all sites, and you see also the red line, that's the WHO high-level recommended limit, and the green line is the WHO low limit. And you can see we, at all places, wherever we measured, we were above the low limit from WHO, and half of these places we were actually above the high recommended limit. And these ranges from the highest notation was from airports and harbors and roadsides, and a bit surprisingly, an underground metro tunnel was the cleanest environment in terms of particle numbers. Furthermore, we have used both air-liquid interfaces and submerged testing to rank the effect of the health effect of the collected nanoparticles, and we have used a toxicity scoring, and here you see an example of scoring of inflammatory tox response, where the more redder the results are, the worse is the situation, and the lighter or more white it is, the better is the situation. And we can in this way rank, for instance, that harbors and airports and traffic sites are worse than, for instance, a metro underground rail platform, actually. The next step was to start to calculate and model. We have done models for Barcelona, Saloniki, Milan, Stockholm, and also actually Leeds. I will exemplify with Stockholm because that is where we have the longest time history of measuring nanoparticles. So here you see Greater Stockholm area. Around 2021, we have roughly 2,100 particles per cubic centimeter on yearly average. And that costs around 500 million euro if we take it into health costs. And these health costs, they are produced by 90% by exhaust emissions from the road sector, actually. And we see, and that is the blue part of the pie chart. We can see the yellow part, that is the harbor effect. And we can see a small fling, that's the airport effect. And we have a close-by airport, but that is mainly internal Swedish flights. And the small part, around 2 million euro, that is the non-exhaust part from road transport, actually, if we talk about nanoparticles. So what can we do about this? Here is one example. If we just follow the anticipated fleet renewal in Sweden and apply that to the city of Stockholm, we can see that just by, if people keep this pace of renewing the vehicle fleet, we will go down from, and that is based on estimation from 2021, so the situation can have changed a bit, but we will go down from roughly 2,000 particles per cubic centimeters down to around 200. And if we estimate further onwards, around somewhere between 2040 and 2050, will the non-exhaust emission levels match the exhaust ones, given this, if we talk about nanoparticles. It's a different story about larger particles. We have also applied different scenarios for this, how we can reduce this further. And on the top graph you see the anticipated vehicle fleet renewal rate here. Can I show? Yes. So here I'm just showing the fleet renewal rate. And the second picture up there, that is an already politically decided low emission zone. All non-electric vehicles will be prohibited from entering this zone. The third one, that is an extension of that zone to a larger part of the city, and finally the fourth one, that is a reduction of the road traffic by 30%. That is already politically decided that is needed to reach the goals of the municipality. And you can see that the different scenarios brings different results in terms of cost and health. The blue bars is an estimate of the health effect, and the red bars is an estimate of the health cost. So we have yearly lives saved. So the blue ones are saved quality lives, and the red ones saved health-related cost. And you can see we need to actually have a rather large zone where we only use electric vehicles or allow the hybrid cars only run on batteries to have a large impact on the cost, and also a reduction in the terms of number of vehicles will also have a large impact of the result. So, general cost-effective measures to rapidly reduce nanoparticle exposure, that is actually by, of course, measuring them, but a rapid renewal of vehicle fleets. So we really go into the electric vehicles and also remove the older ones, the Euro 5 and Euro 4, that are still around there. And introduction of low emission zones. We have also done laboratory testing. So we have checked if both non-exhaust and exhaust components produce nanoparticles, and yes, all of these produce nanoparticles. We see nanoparticles from brake, clutches, tires, third rail, wheel rail contacts in different amounts. And in this way, we have also been able to rank their toxicity. So in the same way as we have ranked the toxicity of the different sites in the cities, we have done this also for the laboratory test results. And we can see here is one example of an inflammatory tox scoring. The more red, the more impact of inflammatory response. The whiter, the less is the impact. And you can see that here we have a large variation in the response from different friction materials from brakes. So the top one is actually a brake material, and then followed by clutches, 2 exhaust emissions, and a second brake material. So we can have a large variation there. We have also looked into if we see secondary particle formation in this kind of laboratory studies, and we see them both from exhaust and non-exhaust emission. And here is one example from a test of a friction material from disc brake, mechanical brakes. And what you see here is a test. We have total concentration. We see a low level of particle emissions. And then when we apply UV light, we have a clear burst of particles. And this is a repeated test of 2 different materials. And you see that the concentrations are all in the nanoparticle range, focused on the smaller size. So if we go to the recommendation, we see a wide variation of nanoparticles in urban environment, ranging from 4,000 measured at a metro underground station to 19,000 in a harbor. We see also that the tailpipe exhaust remains the dominant source of nanoparticles in all cities we have studied, and we see the highest inflammatory toxic scores inside where we have car or ship emissions. So we recommend limit of nanoparticles. We also recommend risk guidance of sources and inflammatory tox scoring, and a reduce or ban of internal combustion engine traffic, both for road, ship, and rail and aviation. So, going back to this, Euro legislation, yes, it has worked very well, but it's still not enough. We still can do more, actually, that can benefit at least the citizens in Europe, in a health perspective. I would like to thank the nPETS partners. Some of them are sitting here. Sissis, hi. All around Europe. So we have our partners from Aristotle University, CISIC, Brembo, IRFRM in Milan, Lund University, Tampere, Karolinska, Stockholm City, CISIC. And also, if you look at the photograph, you see one of Leon team member here is Yuan. We have had several jointly conferences during this period, actually. So thank you.
If you have any pressing questions, please.
Thank you very much. My name is Christian Schmidt. I'm from the German Automotive Club, and I was working also since 10 or 15 years in the meantime in the brake dust area. And I have a question. You mentioned that most of the emissions are getting out of the exhaust, which is clear. And if we come back to the electrification vehicles, so we have only tire emissions and brake dust emissions. Have you ever done, or did you thought about a study to simulate also the impact of connected vehicle driving? So which means with a connected traffic system, so vehicle decelerate only with electrical drives and so on. I think there's also the potential to reduce brake dust emissions and tire emissions as well, so which means speed limits and so on. Did you check that as well?
No, we didn't check all these details, but it's well worth exploring. I totally agree on that.
Okay, thank you very much.
Yes, we didn't go into details on all that subject, but it's well worth exploring further. That. Thank you.
Thank you very much, Ulf. And I take advantage to mention as well, so the NVIDIA database actually, who provides all the data of the research that they did, it's still available as open source, so please don't hesitate to consult that as well. So we move on with Juan Jesus Garcia from IDIADA, who will present you the results of the lOwNoise project.
Good afternoon. My name is Juan Garcia. I'm from IDIADA. I've been the coordinator of lOwNoise. lOwNoise stands for Low Particle Emissions and Low Noise Tires. And basically, the focus of this project is to try to understand and explore the situation that we have from the tire as a source, trying to understand how particles are generated, how do we measure particles, how do we quantify how many particles and the structure of these particles in terms of size and distribution. Also understand how these particles evolve in the environment and how these particles, once they are in the environment and in soil or in the air, they might affect human beings. And the same also not only for particles, but you know that tires are also a problem for noise. So we have also studied in parallel the noise effects that still are occurring, particularly with tires for trucks that tend to be still quite noisy, and they don't explore or I would say exploit one technique which is called randomization, which is very common in the automotive industry for cars, which means that you, for a given car, you can produce an attenuation of certain quality of the sounds and make the sound more, let's say, acceptable. So for trucks, this is not still applicable, but we have explored what would happen if this was done. So you will see the situation. And again, we have moved from, going back. Still learning. Okay. We have explored how to move from the source in terms of noise how the noise propagates and the impact on health, and in which context, basically sleep effects, only sleep effects. So what we have done is explore the effect of tire noise on sleep only. And why sleep only? Because this is very much related to cardiovascular and other diseases like depression, stress, anxiety, and also cardiovascular risk. So this is particularly the scenario we have analyzed. People sleeping in laboratories under very severe control of what is happening with biorhythms, with biomarkers every morning during 5 days. So this has been a very strict analysis of the impact on noise. And in terms of particles, again, how we measure particles, how we quantify particles, how do they propagate into the environment, on the soil, on the air, how much of these particles will affect people, and we have also assessed the level of inflammation that they might produce on lung cells, which is an indicator of how much impact they can produce on human health. So this is what we have done. So this is like a overall overview of the complexity of this source of noise and particles. And the project has been divided into, you can see all the fundamental work packages that take into account this analysis. The most important, basically, work package 2, which goes into tire wear and emissions. Work package 3, microplastics, take into account that tire particles are considered as one subset of microplastics. Work package 5, we did something that was very interesting in the context of the project, and is explore designing and building an airless tire. So an airless tire is a tire which does not have pneumatic, part. So it means that you don't have a chamber, an air chamber. And the mechanical and acoustic properties of these tires change. So we wanted to see whether this could add a particular benefit in terms of noise. So we designed and built an airless tire for a truck, which is the first that we have seen so far, and we then checked whether this offers some potential for improvement. So this was the objective of one work package. And then the analysis for the impact of tire noise on sleep was done in work package 4 in particular. So we have 4 work packages focused on research, pure research basically, and development. So the most important point. So we have a source and this source produces particles. So what is the first thing you do with a source that produces something that is bad? Quantify how bad the source is. And this is what we try to do. And it turns out that tires produce particles, but the type of particles they produce and the characteristic of these particles, the shape, the chemistry, the composition, and also the distribution of the dimensions depend very much, not only on the tire, but also on the road surface on which they are produced, and also how you drive the vehicle, and also what type of vehicle you drive, and also how the circuit is designed in terms of producing lateral forces, acceleration forces, braking forces. So everything affects really tire particles. So we said, let's try to measure tire particles on board in real driving conditions. And then we were very brave trying to do this, and this is what we did. So basically we took a light commercial vehicle, a van, and we built a system trying to catch all these particles in real driving conditions. And inside this cavity, what we did is to try to suck, you can imagine, a certain volume per unit time. So we did simulations, and we assumed that this volume of air would contain on average, a certain amount of particles that then, inside the vehicle, we would be able to analyze with a portable laboratory system for exhaust, for particle analysis. And this is what we did. So one of the main challenges here is that this was built based on simulations. So we did something that was constructed and simulated, but then when we try to implement this in reality, what we found is the level of particles inside, due to the small effects externally affecting the environment, like, for example, agricultural work, the fact that you are driving at a certain speed with lateral wind, the inclination of the vehicle can produce changes, dramatic changes in the gap between the cavity and the road surface. So all the aerodynamics inside are affected. So it was very difficult to have a constant sensitivity between the particles that are generated and the particles that I can measure inside and analyze. So we found that this concept, even though it seemed to be reasonable from a practical point of view, it is not robust enough to get consistency. So this was something that we learned in the project, and then we explored other alternatives. Another test that we did, which was in the same line but much simpler, is with a track. Here what we did, instead of building a cavity, is to put just a very simple probe very close to the trailing edge of the tire and, let's say, sucking air with particles. And this test, what was done in order to find the correlation between type severity of driving and the level and type of particles that you can produce in different roads. We did tests in different roads, public roads, on tracks, and what we found is that, in fact, as many researchers have found, there is a very close correlation between how you drive and how many particles you produce per unit time. So it's not only how you drive, how fast you turn, how fast you brake, how fast you accelerate, road surface again, and also we found how sensitive these methodologies are to external activities like agricultural work, for example, or construction work. This contaminates everything, and you don't get good signal-to-noise ratio. So you cannot really measure in these conditions to get, let's say, safe values, or let's say values that you can use for regulatory purposes. So this is a very important conclusion. These concepts cannot be used nowadays for regulatory purposes. Why? Because they are very sensitive to anything that can affect and not robust enough to get values that can be reinforced. So then we move into the laboratory. This is in VTI, one of the partners, and you can see this is a very nice lab in which you can see it's a track, circular track. Here you can put 4 tires, and you can, it's like a carousel, and these tires rotate at a certain speed with a certain pressure, and what you do basically is to say, well, now the room in which this facility is installed is the cavity where I'm going to measure the particles. So imagine, we seal the room, you have the carousel producing tires, particles, and we will measure inside how the level of particles will increase. So the same room is the cavity on which you will do the analysis. And this is what it was done. And from that, we obtain the conclusions that you are going to see. Basically, this is just the opposite to what you have seen before. It's in the lab, and now what we do is produce particles, we trap them in the room, and we analyze how they evolve. And you can see, for example, important things and relationships that are fundamental in order to understand the effect of tire design in tire particle generation. For example, the hardness, you can see, and the temperature. You see, for example, that it has been shown and confirmed that tire temperature, as you increase the temperature, the tire will become softer, obviously, and the softer the tire, the more particles are going to be generated. So this is clear, this is confirmed. Another thing is, of course, you change the tire, and depending on the tire hardness, you know that summer tires tend to be harder, and winter tires tend to be softer. So in actual fact, you will measure, and it has been measured, that winter tires, which are softer, produce more particles than summer tires, which are harder. So this is obvious, and this is something that is tribology, fundamental tribology. So this has been confirmed. And also the interaction between tire design, and which is hardness at the end of the day, and temperature. You can see, for example, that you change the hardness with different type of tires. As you change the temperature from 25 to 10 degrees, you get less emissions as you reduce the temperature, having a certain set of tires. For a different set of tires, the same principle is observed. So regardless of the tire you have, if you change the temperature, you will have this correlation. So this is something fundamental, we know, but this is very much related to the characteristics of any tire design. What happens with the road surface properties and the tire wear concentration? This is fundamental, and this is like the brother, the forgotten brother. Why? Why is that? Because when we have a tire is always rolling on a surface. And this surface is probably even much more important than the tire itself. And at the moment, we tend to think that, oh, no, the problem is only the tire. No, we are completely wrong. So it's the interface tire road surface that really determines the problem with tire particles. And this is shown here. For example, look at this plot. This plot has been based on exploration, the amount of tires observed at 1 meter from the road, different roads. There are local roads, Rotterdam city, highways, so any type of road. 1 meter away from the edge, from the lane. And you quantify the amount of particles that you find grams per square meter, and on the horizontal axis you have the annual average daily traffic, the amount of vehicles that use this road. So what happens? You get a very nice linear relationship, more particles, more tire wear, depending on, of course, the number of vehicles that use the road. And you see a very nice trend. But we have two roads that seem to have a different behavior. Why is that? It's A2, it's a motorway, and A18, this is, I think A2 is in Netherlands, and A18, I think, is in Sweden. 2 minutes, only. Oh, so I have to go very fast. So basically what we see is that by changing the road surface, you can get a dramatic reduction in the tire generation. What about the concentrations in ambient soil? Well, the concentrations, you see, for example, that as we move away from the road surface, the road surface, then the concentration in the soil decreases. In the ambient temperature, we have measured the levels of particles in cities, in highway, and in regional backgrounds. So there are differences in the environment, and also the particle size distribution. You can see that in general, the sizes of the particles tend to be quite big. So greater in general, the majority of the particles are greater than 10 micrometers. Well, biodegradation, what I can say is that in general, biodegradation produces a certain reduction of the size of the particles. So they tend to become smaller as they suffer biodegradation. And in general, from the point of view of chemical point of view, there is an aging effect, ultraviolet aging effect, results in removal and partial oxidation of organic additives in tire wear particles. The noise. What we have found is noise. The main issue with noise is not just the level, which has been for many, many years, is the transient. So what really wakes you up at night is a transient behavior of a sound that you don't expect, first. The second is that too much effort has been put during the last decades in reducing the decibels, but still there is potentiality in reducing annoyance by playing with tonality. So tonality is another factor that can reduce annoyance and improve the quality of sleep by modifying the tire design. So this is still a niche where we can make improvements in tire noise, for trucks particularly. Okay, tire emission factors. What we see is that the tire emission abrasion is very much dependent on vehicle weight. So as we move into electrification, vehicles will be heavier. We will produce more tire wear. Why? Because electrical vehicles are heavier. As we go from passenger cars to trucks, we will also increase abrasion behavior. So, as you know, for example, as you move for passenger vehicles from internal combustion to electrical vehicles, we get an increase of the order of 25% in particle matter, PM10, based on just the impact of the weight, additional weight from the vehicle. The same happens for trucks and light commercial vehicles. So this is an important issue, is to take into account that electrification makes the vehicles greener, but on the other hand makes them grayer because we produce more tire particles. So we have to play with these two trends. Impacts. Possible mitigations. Well, mitigations can go into the reducing tire particle generation, tire design, can also go into collecting particles. Collecting particles means basically trapping these particles. How can we do that? Basically by using road surfaces with porosity. This is something that works very well. We have shown that, and you might expect a reduction of more than 50% in the tires that go into the environment simply if you use porosity big enough so that the particles get trapped into the road surface that later can be cleaned with special machines. So this is a very nice and attractive option. Another possibility is to collect particles, as I said before, and also another possibility would be to reduce the exposure and treatment of the particles by cleaning. Cleaning is probably a solution that will work, and also the treating of road runoff waters. This is another very powerful action that can be taken. And well, this is the last, the impact policy recommendations. Well, policy recommendations go from tire wear and into the noise. For tire wear, we have that the cost to the environment is unknown because still we don't know the impact, the economic impact of, the cost per, let's say, unit of tire wear pollution. So we need to assess and explore good values of this economic impact of this pollution in order to have proper cost analysis. On-road particle matter and particle number measurements are not ready for regulatory purposes in terms of on-road tests, so they must be in the lab or comparative with using reference tire. This is something that can be done and is done using the convoy method, but not in the way we have done by using only systems on road. Another point would be the results of lOwNoise support the current regulated aberration methodology with a reference tire. Cost-benefit analysis shows a net benefit of reducing the emission factors of market tires. And another point is uncertainty in the cost estimate of the treatment facilities and in the retention efficiency for tire particles and microplasticos in general is a point that needs to be covered. And in terms of noise, what we propose is to revise the legislation in terms of analyzing transients, maybe introduce a measurement of tonality, and recommending maybe the tire manufacturers for trucks to reconsider randomization, which is used for passenger cars, because this adds a very good value to the quality of the tire sound. And that's all. Thank you very much. I'm sorry for being late. Okay. Any question? I wonder if there's any.
Yep. Thank you very much, Juan. So is there any clarification question? Please, Maurizio.
Hello, thank you for the presentation. Just referring to the previous presentation where they stressed heavily the particle numbers, can you say something on the trends that you talked about in terms of numbers rather than mass?
About
yeah, the various trends that you've shown, is it parallel or, I mean, you show that the distribution is extremely on the right. So, out of top of my head, I would say that the particle numbers are not likely to go high, but do you have measurement data on particle number in the various conditions that you've tested?
Yes, we have. Yeah, sorry, the question I didn't.
It's a trend of, I mean, you took some conclusions at the end.
Yes, I understand.
For mass, what are the conclusions for
well, this is
numbers?
The aberration level that we have found. 96 milligrams per...
Yeah, but that's mass.
He was asking about number.
Particle number, PN.
Oh, okay, it will be 4% of 96.
No, number is the part, not mass.
Ah.
Counts. Particle counts.
Oh, I understand. Well, I don't have this on the top of my mind.
But the distribution is extremely skewed. So am I, let's say, is it correct to assume that the particle number will be extremely low compared to other sources per kilometer?
Yeah, I understand. Well, I cannot answer this with...
Sorry?
Yeah, I cannot answer this on the top of my head. Sorry. Yes. Okay.
Thank you very much, Juan. So now I will give the floor to Mr. Spiros Pantis from the University of Patras, who will present you the results of the EASVOLEE project.
Good afternoon. So EASVOLEE is trying to take a look at what happens to vehicle emissions after they get out in the atmosphere. As the emissions are getting lower and lower, what happens afterwards is becoming increasingly important, especially if you go a little further away from the major road or the hotspot. So for a long time, the framework for looking at emissions was, okay, they emit non-volatile particles and they emit volatile organic compounds. It became clear that these volatile organic compounds react and produce particles. And these particles are actually semi-volatile. Part of them is in the gas phase, part of them is in the particle phase, and they evolve. So this framework has carried us for a few decades, but it became clear that it is incomplete. that life is a lot more complicated. Combustion emissions are emitting organic compounds of all volatilities, not only the volatile ones, but things that we call intermediate volatility compounds. They are a small fraction of the emissions, but they are very good in making secondary organic aerosol in the atmosphere. Also, the particle emissions that we have been hearing are semi-volatile. You know, half or 3/4 of their mass can evaporate after they get out in the atmosphere. They change size, they coagulate with other particles. And to make things even more complex, all of these things keep reacting, especially in the gas phase. So you can get things to leave the particle phase, a lot of material to come down, and this makes regulation increasingly complicated. So what EASVOLEE has been trying to do is to take a look at all of these species, starting from looking at the emissions, but going a lot deeper in what is emitted chemically and also the properties of the emissions other than mass. Then to look at the atmospheric processes, the health effects of the fresh, but also of the processed aerosol, to try to build new modeling tools that account for this complexity, and finally to use these tools to provide some insights about policy and regulation. So the project started 2 years ago. We're exactly in the midpoint right now. There are 8 partners, Weizmann Institute from Israel that is looking at health, us fourth in Greece. There are 2 partners from Switzerland, the Paul Scherrer Institute and the company BFH that is helping with emissions testing. 2 partners from France, CNRS, the laboratory in Lyon, and the company CRMT that is looking at emissions under real driving conditions, TNO in the Netherlands, and METNO in Norway. And this is a picture of the consortium in Patras. So the objectives of the project are really 2. First is the scientific half, to figure out the contributions of the secondary particulate matter formation from transport engines in Europe. And then there is the policy part, to look at the impacts and strategies for these. And we're looking at both organic and inorganic particles, at particle number, and both primary and secondary. So let me try to summarize a little what we have done so far and share with you some of the results. For the emissions characterization, we are looking at all groups of compounds from low volatility to volatile, as well as the particle number. We are doing kind of the traditional laboratory testing. And I have chosen this picture because we are looking also at scooters, which are important, especially in Southern Europe, and sometimes are forgotten. We are doing real driving emissions in Lyon, both at large vehicles like a bus and smaller ones. And we had 2 kind of interesting ideas. We have done a month of measurements in the Fréjus tunnel connecting Italy and France, looking at something like 4,000 vehicles, 2,000 trucks every day for a month. And we're looking both at the emissions under these standard driving conditions and the secondary production. And we have just finished a campaign in a big parking lot in Patras, looking at the cold start emissions of something like 20,000 vehicles and the secondary formation from these. So some of the results from the measurements, these are from the tunnel. Overall, the news are relatively encouraging. Here, the different colored dots are emissions expected in different years in Europe, Asia, and the US. And here are our estimates for light-duty and high-duty vehicles in the tunnel These are per kilogram of fuel. And you can see that they are kind of at the relatively low end of what one would expect for the different years. And these are the carbon monoxide emissions, black carbon, ammonia. Overall, there were no unpleasant surprises. It's just that we can constrain the emissions of the fleet under these driving conditions better. Again, what is special about our measurements, and this is from the laboratory measurements, that we just get a whole lot of information about the emissions of thousands of compounds. Each line is actually a different compound from gasoline vehicles, from diesel, and from scooters. And something that may not be obvious, but if you look at the scale, the scooters are emitting 1-2 orders of magnitude more than what the other cars. And these were scooters used in Switzerland, of all countries. So this is something that we are kind of following up on. Secondary organic aerosol formation. Here we are using a number of different tools. Both us and PSI have large atmospheric simulation chambers, and we are looking at specific organic compounds emitted and how much organic aerosol they form. So this is kind of the chamber. We can carry these chambers to other areas. So we have been doing measurements in Switzerland, in France, using the emissions from the atmosphere. And we are also using these oxidation flow reactors that are not as realistic, but they are very robust and they are easy to apply even under real driving conditions in a car or a bus. So the results here is that secondary organic aerosol is extremely important. These are our results from the parking. These are kind of the average concentrations in the parking, the red line. The yellow is we simulate night chemistry, right? Things happen even during the night. You can see the aerosol didn't increase much. And the other 4 bars is the organic aerosol after processing in the atmosphere under sunlight. And this is more and more processing. And it increased on average by a factor of 6. So the processing makes a whole lot more aerosol than what is actually emitted. We have been studying these secondary aerosol. These are actually the raw measurements in the parking. And so the oxygen to carbon ratio, how oxygenated these compounds are. And you can see they vary every day because of the traffic. But when you oxidize them, again, they get a whole lot more oxygen. They change chemically dramatically. And this has, as we will see, health effects. And this is, how much detail we can get, how many carbons and how many oxygens all of these compounds have after they are produced. So for the health, we are doing 2 different things. We are getting the fresh and the processed emissions, and we measure both using cellular methods, the oxidative potential of these particles, but we also expose cells to these compounds to get more realistic health effects. So the results, these are from the studies exposing cells to the particles. And we have been doing 2 different things. We have been exposing lung cells, which is what you usually do, but we have been also exposing liver cells because there are a number of health studies that show that these particles can move in our body and actually reach the liver. So this is the health of the cells with time. The black line is the baseline, and the other colored lines is how well the cells are doing when they are exposed to the oxidized particles. And you can tell that they are getting worse and worse. Actually, we're finding that this chemistry makes these particles more toxic on average. The last part is the modeling. So there we're doing two different things. One is that we are using three different models, kind of the Greek model, the Dutch, and IMEP from Met Norway, which is kind of used for policy across Europe. These models have enough complexity to simulate the chemistry that I mentioned, and we are looking both at regional and urban scales. One of the products of this work, which will be a major contribution of the project, will be a pan-European emission inventory that TNO is preparing that has the volatility and chemical resolution. It will not be just mass and number. And it will integrate both the results of our project, but also of our sister project, PAREMPI, that you will hear later, and the third project that is also in this direction. The modeling, as I mentioned, is taking place both at regional and urban scale. Obviously, if you want to look at a city, you need this type of resolution. This is what the regional scale gives. And the thing that we are also doing is that we are simulating with the same chemical complexity particle number. This is kind of the result from the regional scale for Europe. So some of the results here, this is kind of the current state of the inventory for the emissions of particles in Europe from TNO. But here are kind of the extra resolution. There are semi-volatile compounds, intermediate volatility compounds from different types, from passenger cars to motorcycles. So this is not just mass, it has the volatility of the emissions included. Also, this is our preliminary results. You know, do these things matter? And the answer is yes. This is just organic aerosol from the intermediate volatility organic compounds. This is neglected right now by most models and policy. The black line is the concentration predicted in Paris by our oldest version, and this is the red is with the results that we have so far by EASVOLEE, just from traffic and just for the intermediate volatility compounds, they kind of almost double the predicted concentrations. And this is for particle number that we were discussing. These are high resolution results for Athens from different sources. This is gasoline on road, this is diesel on road, and this is actually shipping because the port of Piraeus is here. And what is important is that in this model, the primary particles evaporate, and also there are other processes like nucleation, etc. So something about the expected impacts to close the presentation. We hope that first, this will lead to better scientific understanding of all of these processes. And at the same time, it will be a step forward in assessing the contribution of vehicles to mass, number, air quality, and health. And we hope that this will provide additional input for policy and to mitigate secondary PM formation in Europe. Right now, all the measurements indicate that as far as particle mass, 3/4 of what we are breathing in Europe is secondary. It's not primary anymore. And this will help to quantify the transport externalities and support future legislation. Thanks for your attention.
Thank you very much, Spiros. Then I propose we move on to Mrs. Paivi from VTT, who will present you the results of the PAREMPI project.
Good afternoon on my behalf. and I'm going to present you sister project of EASVOLEE, and this is PAREMPI, which means is Finnish language and means better. So we hope for better air quality. So the name of the project is Particle Emission Prevention and Impact from Real-World Emissions of Traffic to Secondary PM of Urban Air. And we already heard what this is about, but to repeat, it's not the whole picture what comes from the tailpipe of vehicle or exhaust duct of a ship or any moving vehicle using internal combustion engines. Since after that many reactions start, and all of the gases that comes out from the tailpipe may go through many reactions. Nitrous oxides can react with ammonia to ammonium nitrates, and we have a lot of inorganic and organic components in the exhaust after 1, 2, 3, or 5 days reactions in the atmosphere. And so we want to quantify or at least understand better what is the real whole picture of the exhaust that we breathe. Our project has been running for 2 years, and this is the last year because this is 3 years project. We have 8 partners from 6 countries and 3 million budget. So we have partners from Finland, Sweden, Poland, France, Czech Republic, and Portugal. And since PAREMPI is sister project to EASVOLEE, we are studying many subjects that are dealing with the same phenomena, but from complementary viewpoints. So we also, in PAREMPI, are looking for better understanding of the transport sector's contribution to total ambient PM 2.5. And for that purpose, we do a lot of scientific fundamental research. And we also study toxicity of the exhaust and also of the particles that represent ambient PM 2.5, since the composition affects toxicity, so not all the particles are equally toxic. So inorganic and organic particles may have quite different features. And then also the health impact assessments are being carried out, especially during this last year, and the external costs will be then adjusted and improved accordingly based on the knowledge that will be generated in this project. And then we have, as the final steps, the policy recommendations and scientific report where the policy recommendations will be based on, and also the public database of the secondary organic or secondary aerosols and toxicity, and also related emissions. So we have had complementary measurement campaigns based on the identified gaps in the knowledge, and then we have modeling work package in the project, and toxicity health impact assessment and evaluation of externalities. The complementary measurements have been completed. We have evaluated all the transport sectors from light duty to heavy duty aviation and marine sectors, and also brake wear measurements were carried out. In the light duty measurements, we tested 7 cars in Posmal, Poland, and the cars represented the latest European emission standards, so 2 plug-in hybrid vehicles, 1 gasoline, 1 diesel, then the most recent gasoline diesel internal combustion engine-equipped cars and one CNC car, and then 2 references of the older cars. And for the trucks, we had 2 Euro 6 trucks. The other one was brand new truck, and the other one had 1 million kilometers driven. And these were measured on road in the routes that reach Lapland, and the temperatures varied from -5 to +4 degrees Celsius. And aviation and maritime were simulated campaigns in a laboratory, and our measurement matrix covered 7 different jet fuels, having also renewable components up to 100% SAF. And then in maritime campaign, we had the true real marine fuel, which was used in the diesel generator that tolerates quite poor fuel quality and up to 4,000 ppm sulfur, which is typical for the maritime engines. And we injected ammonia vapor in the exhaust to simulate also future ammonia using internal combustion engines. And we had ash, since ash is one important component in the particles from marine sector. And the measurements covered gases, semi-volatiles, composition of aerosols and particles, and aged particle emissions after secondary reactions with simulated by OFR and oxidation flow reactor, and then SPAMS for the compositional analysis. And for the toxicity analysis, we had air liquid interface-based incubator system that captured the whole exhaust during the measurements. Here are a few examples of the results that are being processed. So all the measurements are completed, but a lot of data processing is ongoing. And as Pyros already mentioned, the secondary reactions, they can produce a lot of particle mass. So the ratio can be 6 or 10 depending on the exhaust source. And here you can see one example of the gasoline vehicle of the latest emission standard, which shows yellow rating for the particle emissions, while there is already none, almost none, in the normal condition immediately after tailpipe. And then here you can see the toxicity incubator system where air liquid interface is used. So after these cells are exposed during the testing, they go to very in-depth different toxicity testings, which are listed here. And we also do toxicity rating system, and in the database that is public, and it will be available soon for the public references, uses this toxicity rating system so that the toxicity, which is significantly higher than the normal case, it is red, so quite visible and visual system. And then health impact assessment and societal costs are being evaluated this year. And then for the modeling work, there is not only modeling, but also aerosol dynamics are being studied. So what happens during dilution and cooling. And secondary organic aerosol formation from some representative semi-volatiles like xylanes are being studied. There is not so much information on that yet. And then modeling for the in European scale and global scale will be conducted so that we know the contribution of transport in the particle formation. And this is then the clips are from the database, and a general view on the upper table shows that even though we may think that we know quite a lot of exhaust emissions, especially for cars and on-road, the table is full of missing data. So the red ones is data that is not existing now. So there is a lot to do, and so far only a few studies have covered the secondary aerosol formation and how much HPM is generated by the cars or trucks or whatever from the transport sources, since the measurements are really complex at the moment and difficult to carry out. But that's why we have one of our targets is also to evaluate the robust measurement system. Then we could have more data from many sources. And then the scientific report will be also compiled and policy recommendations. So our results, they cover the increased understanding of contribution of transport to ambient PM 2.5 emissions, and this robust measurement system, which is being evaluated, and actually a public deliverable will be out soon. And then a novel EPMI module, how we call it, will be a software publicly available where you can you have input of NOx, ammonia, semi-volatiles, etc., and it can estimate how much particulate mass it potentially could produce. And then when combined in health assessments and improved transport externalities, policy recommendations will be compiled. And the outcomes, we hope that the results of this project, which is running its last year now, will be further developed with the other projects, other researchers, and so on, so that the prevention actions of ambient PM 2.5, which is related to transport, could be taken. And then this tool software, we hope that it will be useful also for the policymakers and all, and the decisions would be then based on scientific evidence. And the recommended policies could be implemented. And as the last step, the impact beyond this project would be contribution to the Europe's due to ambitions of Europe to make our transport system clean, secure, and efficient, and to save premature deaths and costs, and open markets also to clean technologies. And we do collaborate with our sister projects, so PAREMPI, EASVOLEE, and aerosols collaborate to achieve these targets. Thank you.
Yes, thank you all speakers for the nice presentations. Maybe before we open the floor for questions, I would like to just maybe try to link a little bit the project and give also the context from a kind of historic perspective. You know, I'm Greek, so I like history, apparently. So I would say things started in 1999. This was coordinating a project that was called Particulates. And it was the first time where, together with PAREMPI actually, so we know each other since last millennium, we were looking whether we need to regulate particles. And then the PMP project, the particle measurement project, started. And they came up with the idea of regulating just the solid particles, and this was not based on health evidence. It was based on the need to introduce diesel particle filters. And particle number was a very efficient and effective measure of introducing particle number. And this is where globally, you know, the particle number came possibly as a measure for regulating particulate matter. And you know, still to the date, for example, the United States, they have never accepted that particle number is a good enough measure, and they still are based on particulate matter, that is mass for the regulation, which is the epidemiologically recognized magnitude for that. So we are quite advanced in that respect in Europe, and China has adopted the same limit, and you know, this has been enforced for diesel vehicles, gasoline vehicles with direct injection. We still have a gap with motorcycles that they have port fuel injection, and there is no particle number regulation for them. And then the question is, you know, since we have that for vehicles and it is effective and it is also being used for non-road mobile machinery and for inland vessels, should we do something like that for shipping, for example? And should we do something for that for aviation? And aviation has developed in a different direction. They have the non-volatile particulate matter. So here there is an inconsistency. And while we had this discussion, you know, what we have to do, then basically we start understanding that, you know, it's not just what the vehicle emits, it's also what happens in the atmosphere, and what is what we call the secondary emissions. And we said now we have the particle filters, but we still do not see very big reduction in particle numbers in the atmosphere. So what do? Then people like Spiros came in, and they said, well, we understand how the atmosphere works, but we also need to understand, you know, what vehicles produce and what are the volatile organic components, the intermediate volatility, the semi-volatiles, and so on. And then basically the question that arises is, you know, have we done enough, or there is still things to do when it comes to regulating specific components? But then, you know, while we were having this discussion, the e-mobility agenda came in, and they said we have no exhaust anymore. So since we have no exhaust, you don't need to do anything about that, but you have to look on brakes and tires. And brakes are easy, and electric vehicles do not have big problems with brakes because of regenerative braking. But for tires, we still have problems, as we've heard from Jesus. Electric vehicles are heavier, they need larger tires, and we also need to understand primary emissions from tires, secondary emissions from tires. Mauricio was asking particle number from tires, still the same for brakes. So I just wanted to connect all of the programs. I should say I was impressed that Ulf was brave enough to present monetary health impacts of particle numbers. I mean, this is already several steps ahead of what other people are doing. I hope I didn't confuse you more. I just wanted to say what is, let's say, the whole storyline on these particle numbers, and to finish up by saying that, you know, we are going to have also alternative fuels. Päivi mentioned ammonia, for example, nitrogen oxide, so also non-organic components that might form secondary particles. Therefore, there are still open questions out there that we have to regulate in the context. And now, after this, I'm also expecting, you know, the questions from the audience in that, let's say, scheme of things. I mean, where do we see we need to guide the Commission in further regulation of particle number of particle mass in Europe? That's the basic idea. So, questions? Probably it was a very long introduction to questions.
Thank you, Leonidas. It's not just a question, it's just a statement. Okay, as you said, if you have particle numbers, then you need, for internal combustion engines that emit particles, the filters are a solution. So you just eliminate particle numbers, except in the case of tires, maybe where what we have seen, particles are at the micron level or 100 microns, where of course, the number is not that important unless they emit nanoparticles, which we do not see and we don't expect. So the health effect of these particles are not that for humans, for the lungs, but mostly for the nature, for the soil, for the water, and the microplastics, and so on. So I would see that particle number regulation is the solution also for cases where this does not exist, for example, the motorcycles, as you said.
Any comment maybe any of you on this? Okay, thank you, Dimitri. Yeah, please.
Thank you very much for all the presentations. They were quite impressive, actually. This is Samaras from Aristotle University in Thessaloniki. I have a question to, I guess, basically Ulf, definitely Päivi, as well as Spiros. This was not touched upon very much by Juan. Do you see that toxicology can be taken into account in the future regulations? Or is it sufficient? This can be a multifaceted, actually, question. One is, do we have enough tools to do that? The second is, toxicology takes into account only short-term effects. This is what is being quantified, at least as far as I understand. It doesn't take into account, at least at this basis, the longer-term effects. So, do you have a suggestion or some recommendation towards regulation into how to take into account toxicology, toxic effects, I should say?
Who would like to answer?
Let's see. Can you hear me? No? Can I get
maybe now, Spiro, check again.
So for particle mass, this has been, I don't know, the multiple billion dollar question, right? The fact that all the epidemiological studies correlate for fine PM and health, but when you look at components or you look at sources, the results are all over the place. Some studies see effect, some studies don't. And, this has been perplexing. I mean, my advice to the US EPA, I have spent half of my career in the US, has been that somehow our toxicological tools don't work well enough to see the differences. And please don't put all your eggs in the same regulatory basket, right? Don't just control cars or organics or sulfate or nitrate. Make sure that you reduce all the sources. And it may not be the most efficient, but good things will happen. And, the medical community results support this. I mean, I spent 15 years in Pittsburgh, that used to be the dirtiest city in the US. Right now, it actually satisfies the low PM 2.5 standard of the US. It has 6 micrograms per cubic meter. And the medical colleagues can actually see the health benefits. So it has actually worked, not just from a regulatory standpoint, but the health of people in that area has improved. And this was without the toxicology. So yeah, the hope is that toxicology will help us, because to move further, now that things are getting cleaner, is more and more expensive. So keeping the strategy of reducing everything will cost a whole lot. But to be sincere, I'm personally pessimistic, because I have seen 3 decades of effort of superb colleagues that have not been able to add. So I don't have the answer why it doesn't. It should. But maybe, the human body is so complicated, and things that are not toxic are helping carry the toxic material to places that can cause damage. Maybe the effects are small enough that we cannot tell the difference. But I'm pessimistic that we're moving forward. Is toxicology going to win the day? Right now, I would bet against it for this decade.
Maybe Ulf wants to first. Yeah, maybe.
How do I, can you hear me? Yes, good. Yes, what I would say is, basically when I talk to industry, they see a challenge when new regulation are implemented. And that is, yes, we have to replace components. We will have changes in tires due to new regulation. We will have change in brake system due to new regulation. Even if we are electrifying, we will have as a safety system probably mechanical brakes. And then they ask, but do we sub-optimize in any way? Will we start to generate more microplastics if we reduce the PM factor from brakes? Or will we release more toxic particles or gases when we change the friction materials? And in a way, a yes or no answer there can be good actually to try to test for short-term effects. I'm not saying that it's ready for perhaps for regulation, but to be able to study the toxic effect in short term, and also to be able to say, yes, at least we don't put anything on the market that is more inflammatory or more cancerogenic. I'm an engineer, so I can only rely on what the people in the medical sector tells me what we can do, and there we are. I'd say today, if we follow the same protocol, we can start to rank and say that yes, this seems to be worse in many perspectives, or not, or we are on an even standard. Yes, this is even less inflammatory.
Okay, maybe. Can you hear me? Yes. Okay, in the transport sector, the toxicity studies for decades have been trying to figure out whether the black carbon is more toxic or organic fraction of the particulate matter, and it has been really difficult research area, and I don't believe that the answer is still resolved. But now we are entering in the new type of particulate matter also, so we are going to have more and new inorganic compounds in the particulate matters like ammonium nitrate. When ammonia is present, then it can be formed, otherwise it can't be formed. So I don't know whether these changes are then a little bit higher than the earlier particulate matter mix. So we will see, and one of the issues that is confusing that the different toxic endpoints give different results, and maybe that could be also accepted, that some are inflammatory, some cause genetic alterations, and so on. So yes, this field is, I'm not toxicologist, so I cannot tell, but it is really complex. And maybe one more point is that the plug-in hybrids will be one big topic when talking about secondary reactions and so on, since there will be continuous flow of starts of internal combustion engine. So there is a lot to do even to know the particulate matter emissions from the tailpipe.
Thank you very much for the interesting presentations covering air quality and particle emissions. I saw the picture of the city where the air quality and the particle emissions and the non-exhaust emissions also getting more and more important. The question from my side is, as we are getting down the particle emissions
and we are fine-tuning all components, are we coming to a point where it's something like right-sizing the topic and looking for not only regulating the emissions, but also adding some equipment that will clean the city or will clean the road and giving some credits on improving the air without only focusing on what's coming out of the tailpipe, but looking for the regulations to have something that can compensate or bring that in the picture as well, to have an overall better air quality in the city.
I mean, I can try to answer that because the first exercise that I give in my air quality engineering class is, what it would take to clean the atmosphere of a city. And some of you in the audience may be aware that a few years ago, one of the Chinese cities built an enormous chimney that would use kind of solar energy to help the air through, and would actually carry a significant volume of air, and would actually remove 80% of given pollutants. So the engineering calculation is, okay, let's assume that we will use this chimney, what it would take to clean the atmosphere of Athens. And the answer is the gross domestic product of Greece. Right? So the challenge here is that the atmosphere has enormous volume. I mean, we don't appreciate it, right? I'm a chemical engineer. I teach students to build reactors, and they build, 5, 10, 100 cubic meters, and you look at the atmosphere of a city, and it is enormous, and the wind keeps blowing, and removes what you cleaned, and now brings new one that you also pollute, and you need to kind of make it, to clean it again. So I'm very, very pessimistic of the solutions unless we talk about very specific enclosed environments, right? A hotspot, a tunnel, some other environment in a major road. So something where the volume is reasonable, because it's enormous, the air that you need to clean. After we unfortunately release the pollutants to the atmosphere, they are very, very difficult to capture because of dilution and volume.
Can I comment also? No? Yes, thank you. Yes, I can agree on the enclosed space, and I can actually see this happen also now. Now, both Sweden and France locally has introduced recommendation for air quality at underground railway platforms, public spaces where people stand and wait for the trains underground. And if you look at the new design of underground platforms now, they all include filtering solutions, because that is what is needed today, actually, to reach these levels that are in these recommendations. So I can see that, and that is an example of a hotspot for larger particles if we talk about PM10, for instance. But further on, road tunnels, yes, and I have an example where I had my students calculate on having a service tunnel close to a road tunnel used as a bicycle lane under Stockholm, but that would have cost energy of a small nuclear plant, unfortunately.
First of all, also thank you very much for these nice presentations. I have the following question, and this is to Juan Garcia. you know, we have talked about non-exhaust emissions. They are getting much more important because electrical vehicle we do not have combustion engines anymore, and so on. And there's also a good point regarding Euro 7. So the regulation says that we only take care for particle mass and not particle number, and usually it is also much more important how big the particles are, and so on. And my question is, in your presentation, you said that winter tires emit more emissions, which is clear because the rubber is softer and so on. I mean, in Germany, it's not allowed to drive in the winter conditions with summer tires because they are harder, the friction is not such good, and so on. Braking distance is getting longer, it's not safe, and so on. And I mean, but there's no rule which regulates that you have to drive in summer, also with summer tires, yes? And there are a lot of people which are using winter tires in summer as well, and so these tires are worn more and so on, and we all know that all the ice in the Alps and so on is full of tire emissions and so on, which is crazy, right? The ocean as well and so on. And what do you think? Does it make sense if there will be any regulation which does not allow anymore to use winter tires in summer and so on? And the next question would be, is there, you know, tires, you could buy them from Michelin, from Dunlop, from Goodyear and so on, or even from Goodride or stuff like that. So these are China tires, and they are not the best, I will call it like that. So they burn even more. And I mean, we all take care of the OEM's emissions, also of the emissions of the normal vehicle, which are getting out of the plant. But on the aftermarket, nobody takes care of that. And that's my question. What do you think? Does a regulation make sense for aftermarket products or not?
Yes, it works now. Yes, I think obviously, I think the main issue for tires is really safety, right? So if you don't compromise safety, I think it really makes sense to control tire wear and particle emissions. But first should be safety. Safety standards should be preserved. In terms of also legislating and controlling the aftermarket is also fundamental, I think. Otherwise, you might spend, you know, a very important part of a vehicle using the wrong tires, no? And also one thing that we have found is a huge dispersion in the values that you get of tire wear between tire manufacturers, which is very much related to quality. You know? So depending on the quality of the tire, you will have more tire wear or less. So if legislation can really help reducing this dispersion and also assure that the average quality of tires will improve, which will work for safety. So I think in legislation, the aftermarket also will help, and not only increase safety, but also reduce tire wear and particle emissions. So I think it's very positive. But also in combination with that, we should not forget that the tire produces particles because there is a friction with a road surface. And this is neglected so far. We always talk about one side of the problem, but this is a mistake. It's a tandem problem. And if we are not, we should think in terms of a tandem problem because the change is so big that otherwise it's a wrong approach. We have found that you can get benefits of more than 50% simply by changing the road surface. So it means that it doesn't make sense to put only pressure on the tire when the tire is abrade because it's rolling on a road surface. So I think you should look at the problem as a combined problem. It's made up by a tandem of two factors. And legislation, I think, should somehow progress and be aligned in both. So as you think about putting legislation on tires, you should also act and think about legislation on road surfaces. Because when you solve one or improve one side, you should also have the corresponding improvements on the other. Otherwise, you will not collect or reap the benefit of regulating one side. Do you understand my point? So any action should be in parallel and coordinated so that they will end up in a good scenario to reduce tire wear on both, on a combined action of two elements which are interacting together In this way, we will get much better results in reducing tire wear and tire wear particles, I think. Okay.
Well, thank you very much. Yes, one point, the concrete you said already, low noise concrete on roads and so on, they are helping as well to reduce the road surface.
Yes.
Yeah. Thank you.
Yes, thank you. I would elaborate on the last thing because, yes, that's in principle true. But tires are designed for the whole of Europe, if not for the whole of the world. And in Europe, how many needs for different surfaces do we have? Many. The road down in Greece is not the same that, the structure, everything that you need to have for safety, exactly what you said, in the northern countries. So what you say, in principle, is correct, but the moment you consider the variability of the requirements for safety on the roadside and the durability of the road, which is also an issue that the question is what you optimize for. The moment you start looking at the number of variables, I have some questions. Another point which is related to tires from the question there is you show a graph where the distance where the particles end on the ground is basically 10 meters. So also on this, these are not particles that stay in the air. They drop dead meters from the road. So also the, let's say, the impact later, on one end, let's say, the impact on the earth, if they are not even inhaled, because they drop dead in meters, that cannot be a lot, and that's why I was asking about the numbers, because those stay suspended, and therefore it's those that I would like to know how many they are and where they go. And the second point is the countermeasures, let's say, are different if they stay and float in the air for a long time and can go far away, but that graph says that's not really what happens. And therefore, also for the microplastic issue, I would like to know the fate of the particles because of that.
Okay, thank you, Mauricio. And you are right, this particle number, particle matter issue is, as you've described, trillions of particles of no mass that go everywhere versus a few large ones that are very local, yes. Okay, we have 9 minutes to go, and one of the questions that in the end, as session co-chairs, we would have to summarize is what would be recommendations for further research. So I would like to ask each of the presenters to tell me, based on the results of the project that they coordinate or coordinated, what would be a single point of research needed to be done. I know there could be many, but what would be the priority here for from each of the projects? Can you start, Ulf?
No, you can hear me? Yes. I will actually follow up what you answered in the previous discussion. I see a need of actually, when we implement like legislation for tires, that we actually test this on all this variability. How will this variability affect the results we get, both in terms of gases, secondary formation, and particle number and particle mass? Because I agree totally that we have a large variability. We have softer tarmac in the north than in the south, but we have bigger stones in the road due to that we use other tires compared to the south. So there is a large variability. And actually, I think it would be very interesting to study both for light-duty and heavy-duty tires, the impact of this variability on secondary particle formation, gases and particle number and mass. Thank you.
I think from the point of view of the experience in lOwNoise, what we learned is how extremely difficult it is to understand the real mechanism of tire wear generation and tire particle generation on board conditions, which is the real thing, you know. And trying to understand this situation and requires proper measurements. We need to be able to be measured with more accuracy and understand better what we are measuring and where we should measure. Because what we have found is that you cannot control the process. You cannot even understand what the measurement means sometimes. So this is, I think, a very important point to understand better this interaction we are talking about, interaction between tires on a real road surface, driving in real conditions. So we need to understand the reality, and we need to measure and understand the measurement. So at the moment, we don't really understand what we get in these conditions. And the variability is huge. So that's a very interesting area of research for us.
If I had to choose one, it would be to close the gap between our top-down and bottom-up approaches of what is out there. You know, the current models in Europe underpredict the secondary organic aerosol formation. There is a lot more, even in the winter, in places with clouds and no sunlight than we're estimating that it should be. And actually, for particle number, we're overdoing it. The models believe that there are more particles due to chemistry than they are. I'm kind of oversimplifying, but this means that we're missing some potentially critical pieces of the puzzle that now that everything is much lower can push us in the wrong regulatory direction and waste resources.
If it was possible, I would like to generate more data to find the relationship between different technologies and the ambient PM. We started now with these projects from the situation where we didn't have many studies which would address these issues from modern technologies, transport technologies. And then one of the focuses could be on the plug-in hybrids, which are quite important at the moment, and it seems that there is something to do. So this issue of increase in emissions when the internal combustion engine starts many times should be prevented somehow. So there should be something to reduce the emissions at those moments. So to point out one of the technological questions that should be studied more. And maybe then on the tires, would be nice to have also results when winter tires are used on snow and ice. So whether the particle emissions would be equal there.
Thank you. So I've noted all of them and will transfer them in the report. I think if I can also personally say my opinion, yes, I would agree. I would also like to stress the impact of new fuels, especially we know very little about particles from hydrogen combustion. We know very little of particles from ammonia combustion. Also, methanol, well, one would say methanol does not produce so much black carbon, but then it has impacts on lubricant oils. So we don't know what the impact on lubricant oil is and what kind of particles. So I will share your opinion about technologies if we introduce fuel technology as part of the equation. So I think there are still things to do. Dimitris was a little bit more optimistic that we have solved the problem, I think, with particle number, but maybe there are some gaps. Yes, when filters are there and when they work. I would also say, I mean, one gap that I have in my understanding that it is in the science regulatory framework, is that we use different definitions in the different sectors. So we use black carbon, soot, non-volatile PM, particle number, PN10, you know, maybe also with the help of projects like EASVOLEE and PAREMPI, we need to also start maybe creating some definitions that should come from the atmosphere and find application to the technology level. Things have been done a little bit scattered so far. I think maybe we need to come closer together and start giving some definitions in what we are doing so that we can communicate better. I think it's time for coffee, isn't it? Maybe you have the final word from your side as well. So thank you very much for the participation and the active discussion, and to all speakers.
And indeed, yeah, big thanks from my side as well to the participants and also to you in the audience. So next on the program is a coffee break for half an hour, and then you have the next sessions on the screen as well. So depending on the session where you registered, you can go to the meeting room. Thank you very much.